All right, so here we are. So we want to find the extreme values of this function, f of x, on some interval. Now, we're going to come to call those absolute extrema. So we have an absolute maximum and an absolute minimum. Talk to me about that. Where are they?
The y-axis, the absolute.
Well, no, I want to find the extreme values, meaning I want to find the biggest values of the function, the biggest y values of those, right? The values of f of x are the y values.
There's the top of the curve.
So up yonder, there's one, right about there, right? That's what we might call the maximum, right? The absolute maximum.
Minimum.
And where is the lowest value of the function on that interval?
Minimum.
Where's it going to be?
A.
At A. Yeah, right there. That's our absolute min. Okay, good.
Let them in.
Now, why is that?
Instead of like down there.
On the interval, yeah, we want on this interval from A to B. We're restricting ourselves. So in other words, we could go over and let's just do this. Let's just do, the function still exists there, but we'll just kind of make it dashed to indicate that that's, we don't really care about those parts.
That's a good dash line.
Okay, isn't that good? That's right. All that specialized training we had. So on that solid part of the curve, we found the highest point and the lowest point. So in terms of an ant, what does that mean? An ant walking on the function. Yeah, that's the highest the ant could get right there. The highest the ant could get, and that's the lowest the ant could get if he's restricted to only be on this interval, right? Okay, now that's right. I mean, that's, you got the right picture in your minds. Now let's next step would be to turn this into a mathematical definition of an absolute extremum, a place where the function is at its biggest or smallest on an interval. Well, let's define absolute maximum. Let's say that, I'll get you started on this. We'll say that f of c is an absolute max if and only if, what is going on? What has to be true? Okay, so yeah, now you told me this stuff. Now we got to put it into a mathematical language here. You told me that it's the absolute maximum if it's the highest point, meaning the value of the function is the greatest, right, for all the x values on this interval. So how could we say then that
Is that of this graph here, that question there?
yeah, we're looking at on any graph.
Well, I mean from the intervals of A to B.
Yep, A to B we're saying. Absolute max, I should probably say that, on A to B.
Dot is C.
Say it again?
C.
Yeah.
Yeah,
Well, in this case, that would be C, wouldn't it? Right? That would be the value of C we're talking about right there. Okay. And what's in that? The value of the function there, the coordinates would just be C, f of C, right? So what's true then of f of C? How do we say that? Okay. If f of C is greater than what? Yeah. Now, how many other points is on that? How many other points are there on the function on that interval? Infinite. Yeah. Okay. So f of C. Somehow we have to say that. Somehow we have to say that y value at the point C f of C, that's the highest, bigger than all those other infinite ones. So how could we say that? It's greater than f of A through f of B is what we really have to say. We have to think of a way to say that. How about if we said is greater than f of x when C is greater than or equal to A and less than or equal to B.
No, wait. First one's A.
Good.
Yeah. Right? Does that make sense?
one?
That's supposed to be, I'm sorry, that's an X, not a C. Whoops, gotta fix that one little thing.
Oh, okay.
Right? Where X is contained on the interval, the closed interval between A and B, then f of C would have to be greater than all values of X for which, other than C itself, right? So we got to make one other little tiny change to that for right, where C is not equal to X. Does that make sense? So all the other X values are going to give us functional values less than f of C. Okay? And then obviously, how can we define an absolute minimum? Same statement, right? Except you just got to flip that sign around, right? In this case, we'd want the value of C that's going to be less than, where f of C is less than f of X, for all the X values on that interval other than C itself, right? Okay, good. Now let's just look at some pictures, and we're not going to get specific at all. I just want you to look at these pictures and tell me what's going on. I want you to identify the absolute maximum, the absolute minimum, if they exist, or maybe they don't.
How about this? Sorry, yeah, sorry.
Let's look at this. How about okay, what's the absolute minimum? Is found at X equals what? Everybody agree?
Yeah. Well,
Okay. The absolute maximum is found at X equals.
But a max have to be times an X.
What's going on at the other endpoint?
Could we put the B negative? Could be
Okay. Could we put the B negative? The question is, could we do this? Could we do B minus? Well, that's the question we're
as
asking.
it approaches B from that side.
Okay. Okay, but what point is that at? You see a problem there? The absolute maximum in this case doesn't exist, does it? It can't exist. Because no matter what value you say, if it can't be at B, if you're saying it's just at that value, next to B, well, of course there isn't one, right? That's where a limit would maybe be applicable, and that's what we're trying to do.
Yes.
But a limit doesn't work here because I can't get a value for that. If I put in something like B minus, what that really means is the limit of X as X approaches B. But that's not a value, right? I can't plug something into this, and I can find out that when I plug A into this function f, whatever it is, right, f of A is going to give me back an actual value. But I can't plug B in because the function doesn't exist there. And if I want to pick a point that's very close to that, of course I could always find a closer one. If I had to say, and this takes us back to, hey, Matt, could you guys, if I want to, if I'm cutting my distance to the door in half every second, I'm never going to ever stop. Right? I can always, assuming we can subdivide space infinitely, I'm always getting closer. Same thing is going on here.
So just don't put anything.
So yeah, so it doesn't exist. Absolute max, there is none in this case. It's undefined. Okay? Because there's no point that the ant could stand on and say, aha, I'm at the highest point. Right? He can always take smaller and smaller baby steps and approach that pole. Okay? So what about this one? Same questions. Okay, where's the absolute max?
At the vertex.
It's C. That's C.
That's B.
Oh, B.
B. Good. Makes sense? There's our max. Minimum?
There's
C.
none. There's none.
There is none. Because C, now look, if I can see why C people would maybe say C. But if I draw a horizontal line over here, I've got a whole range of values right there that are lower than f of c, aren't they? But there's no lowest value because it's an open endpoint. Right? Now, if I filled that in, then the answer would be C, clearly. Right?
If you fill that
I mean, A, sorry. A, whoops, A. If that were filled in, but it's not. Okay? How about,
Wait, so there's no. Wait, so there's a maximum.
yes. Yeah, there's a maximum, there's an absolute maximum at x equals b, but there is no absolute minimum.
It's really confusing.
Is this just?
There's no minimum because then you can't go back.
Right. It's a weird deal. But that'd be like, just like saying, what's the closest point I can get to the door? And there is no closest point.
Yeah.
All right, one more. How about,
It's really thin line. You are eating some weird candy canes. That is
Never mind, that's not a candy cane.
that's an asymptote. So I want to know, I'm not going to try to put points up here. Can you point to a spot that is an absolute minimum of that function?
Yeah, bottom of that curvy thing.
Well, that's an asymptote. That's infinitely far down there.
There's no.
No.
So there isn't one.
Neither of either.
Right. Is there an absolute
Doesn't
maximum?
make any sense. But no.
What if I cut it off?
Neither of either.
What if I cut it off right?
Well, it depends. Is it open
What
or
if I
closed?
cut it off right there? Whoops, right here.
It would be maximum, not absolute, right?
Oh, yeah, there it is, right there.
Then I agree that point. Whichever one of those is actually higher would be the maximum in that case, right? All right. Good.
How would you find with this 500 here?
Well, we'd probably, presumably, this question would only be interesting for calculus if we knew what the function was, and we could just evaluate the function for that value of x and that value of x and see which one was bigger.
What's the function really?
Oh, shout out's a weird one, isn't it? Okay, so then, how about this? What could you tell me about this situation? What if we had, let's say, all I'm going to tell you here is that there is a strong calculus blizzard, winter storm warning, a
It's not going to.
eight-dimensional winter storm warning that's blowing in.
It's gonna show up.
We'll never see it.
Math isn't real.
Not the way the assumption is supposed to be coming.
And the ant knows for certain that he can stand on the function there at a f of a. Okay? That point exists. And he knows that when he gets to the other side of the function, he's going to be right there at b, f of b. Furthermore, he knows that the function is continuous everywhere in between. Now, what does that mean if it's continuous everywhere in between?
It doesn't stop. Or it doesn't break.
Doesn't break. I never pick my pen off the board in describing the path the ant is going to walk. And it is a function, right? So it doesn't violate the vertical line test, let's say. What can you tell me about the existence of an absolute maximum and minimum?
Let's say B.
Well, we don't know. We don't know what the path looks like.
Oh, yeah, because it can go up.
But you can tell me something crucial,
That's
very
what
important
says
about it.
It is restricted.
Say it again.
between the-
Yeah, they have to be there. Yeah, an absolute maximum and an absolute minimum must exist.
So what if there's
If the endpoints are defined, it's a closed interval.
You'd have to.
Okay, oh, you got to get this. Everyone, focus on this for a second. This is a big one. So we know it's a closed interval because the endpoints are included, right? So on the interval, in other words, if we say on AB, if the function is continuous, then we have to have a highest and a lowest value, don't we? Because if the ant's gonna describe a path that starts here and ends here and he never blinks out of existence, at some point on that path he has to be at the highest point. That might be a shared point. There might be 2 points that are equally high, in which case they would both qualify as absolute maxima. But it has to be there, doesn't it? Now there's a bunch of different possibilities. Maybe it goes like this. Maybe his path looks like that, in which case that would be the absolute minimum, and that would be the absolute maximum.
No, that's pretty close.
Oh, no, that's the absolute
Yeah.
maximum. Sorry.
Incorrect.
Whoops, there's the maximum, there's the minimum. If he were to walk a straight path, a relatively straight path, there's the minimum, there's the maximum, right? Make sense? Okay. If he did something like this, there's the maximum, there's the minimum, right? But it has to be there. Okay. If it's a continuous function on a closed interval, they have to be there, right? Okay.
Yeah, when do we not know what's happening?
When do we not know? Well, here's an example.
He doesn't know.
No, I'll go. What if we're looking at, let's say, let's say that we've got an iceberg is. This is going to be a strange one. That's a little too weird. Let's see. Let's say we've got.
What's up with this chicanery oil? You should have heard Ms. Mitchell pronounce chicanery this morning. What'd she say? Chicanery? Chicanery?
Connery.
Yeah.
Maybe there's another pronunciation.
Yeah, like
There's lots of those. If you watch the Scripps National Scholar, you know
Yeah. Okay, so here's an example. Let's say that we're going to look at the we're going to look at temperature. We're going to look at temperature as a function of time. Okay, so let's say that we're going to start off at 7 p.m. tonight at the start of the winter storm warning.
Oh my God.
The temperature is going to be at exactly I don't know, it's going to be about 34 degrees Fahrenheit right there. Okay, now we know that tomorrow night, at the end of the winter storm warning,
It's going to be a little colder. More cold, if you will.
okay, we know that it's going to be
31.
31 degrees.
Okay, Lathan, sure.
Yeah. Okay. Now, what can you tell me about the temperature there? Is there going to be an absolute maximum and minimum temperature between those two?
Yes.
Of course, because the temperature function has to be continuous. There is no conceivable way that the temperature could do something like
There's no temperature.
What if the law of antimatter?
like that, right? That can't happen. The temperature, by definition, is continuous.
All of a sudden, it just gets colder.
So you know that it's going to be a continuous function. So we can absolutely guarantee, without even thinking about it, that there is definitely going to be a coldest temperature and a hottest temperature on that interval. Well, then that mixes things up just a bit.
What did you say?
Just a bit.
What if there's antimatter? Awesome.
Okay. All right. Next step. Next step. So now what we want to do next, and we're moving towards something really cool here. What we want to do next is we want to relax the notion of being on a closed interval. We're going to just look at the topography of some function. Let me put that phone away. Oh, look at the weather. Well, we'll check it again. Sure. Okay, so now let's not restrict ourselves to being on some closed interval. Let's just look at the topography of a curve, just in general. Okay, so we're going to say we've got something like this. Okay. Now, can I say for certain that this is the lowest point on the function? No. Can I say that that's the highest point on the function? For sure not, because it looks like it goes higher over there. But I can say something interesting about that point right there. What do we know about
Direction
that
does
point?
change.
What do we know about that point right there?
It's
Okay, it's the highest in that area. And that, locally speaking, that's how we'd say it in math. Locally speaking, it's the highest point. Okay, so what we call this now, this is what we would call a relative, sometimes called a local.
Like Cabbage Hill,
So, relatively.
maximum.
you said like.
So describe that in terms of an ant.
He's gonna have to walk.
When an ant is on a relative maximum or a local maximum, the book uses the word relative. What's true about where he's standing on the math function?
It's relatively high.
He's relatively high. In fact, he is relative to the points around him, relative to the values of, say, x in the neighborhood around him, his point is the highest. That's not to say if he looks out way yonder, he's not going to see a point that's higher. But in the vicinity, locally speaking, he is at the highest. Now, what does that translate into in terms of a topographical feature?
I don't even know what topographical
A hill.
means.
It's a hill.
You're right, it is.
Call it a butte, call it a mountain, call it a hill. We'll just call it a hill. It's
Call it
going
a
to be,
misty mountain,
it has
please.
to be a hill shape, doesn't it? If you're going to be at the, if we're going to be at the relatively highest point, that's a hill. Now, I can say that this point right here is what? Yeah.
Yeah.
That's a valley, so it's going to be a relative minimum. Okay, there you go. We had that one in, didn't we? Yeah. Okay, so we got a relative minimum. Now, these things they could be nice smooth curves like this, or they may not be. They might be.
What are you racing for? What are you? It's the ocean.
I'll show you. Or they might
There's a
be.
point.
Maybe they look like this.
Yeah, there's the cusp right there.
Now, that is still an example of a relative maximum, right? As is that. Okay. And that would be a relative minimum. So they could be sharp, or they might be smooth. Okay, let's look at a couple specific examples. See if we can see what's going on with those in terms of the calculus. Let's take a smooth example. Let's take the example, how about, let's pick one right out of the book. Let's take this guy.
Seize upon this local word. All about that. If you were listening, never on your phone. I know. Wait, is that a cusp or no?
No, not a cusp.
Okay.
No, it's supposed to be nice and smooth.
Okay.
So this is the function f of x equals 9 times the quantity x squared minus 3 over x cubed. Okay? Let's look at the derivative of this thing. If I take the derivative of this, now what should I do? Do I want to use, well, you tell me.
Product.
I could use quotient rule,
You should use
but I could use product rule also. I could move this, I could rewrite this as 9 times the quantity x squared minus 3 times x to the minus 3, and pretty easily make that into a product rule thing, right? And so if I'm going to differentiate then, f prime of x, I can leave the 9 out front. And then, what do I get inside? So, first times derivative of the second, so that's going to be negative 3, negative 4. Okay, plus x to the negative 3 times 2x. That's 2x. Okay. So let's see now, we want to probably factor out the greatest common factor, right? Which would be what? Looks like x to the negative,
There it is.
well, I got, factor out the greatest common factor means the smaller of the two. So what's smaller?
3. 2.
Negative 4. Is less than negative 4 is less than negative 3.
It's negative 4.
Okay, so we could factor out then, if we pull out, we got a 9 already out there, we got an x to the minus 4. What are we
That's
left
a
with?
lot.
So here we're left with negative 3 times x squared minus 3, and that whole thing got pulled out, right?
Yeah.
And then over here we've got plus 2x, and yeah.
And 3 you got the extra.
Because I've got an x to the minus 4. See, I've got this whole term, and I really could have combined these if I wanted to. But I've got x to the negative 4 and x to the negative 3. I'm going to factor out the smaller, the lesser power of x. So I'm dividing out an x to the minus 4. Well, x to the minus 3 divided by x to the minus 4, factoring is division, right, is x to the negative 3 minus negative, aka plus 4, right? So this part right here just gives me an x, and then I have an x there also, so x squared, right?
You said about that one more time.
Sure. This is, when I factor out an x to the negative 4, I'm going to get back an x to the positive 1 from this guy.
Oh.
Right? Then plus I've got another x, which gives me an x squared on that side. And then that term. Okay, so now we can turn this into, look what I've got. I've got a fraction. This is negative exponent, so it goes to the bottom. On the top, I've got 9 times negative 3x squared plus 2x squared is the same as negative x squared, right? If I distribute that and then add it to this guy, that term, right?
Yeah.
And then I'm going to get a positive 9, so 9 minus x squared.
Where'd you x to negative 4 go? Oh, okay.
Okay? So that's my derivative.
You're right.
F prime of x equals that. Okay, so
Yeah, what about the 2x squared?
When you distribute it, yeah.
well, yeah, I've got negative 3x squared plus 2x squared is negative 1x squared, right? Okay.
Sure, you said it.
The negative 3 times negative 3 is 9. Now, notice in my original function that I can't divide by 0, and so as you'd expect, I've got this asymptote at x equals 0, right? But what's going on with, with this derivative? If I want to know where the derivative equals 0, and I've got a fraction like this, where is a fraction equal to 0? When the denominator is 0, right? Okay, so we've got something like this. We've got f prime of x equals 0 when the numerator is 0. And what's the part of the numerator that's going to go to 0? That constant we don't really care about, right? It's going to be this part, right? So it's going to be when
So it's 3?
9 minus x squared equals 0, right? So that's when x squared equals 9, which is when x equals plus or minus 3, right? Okay, now, we didn't even bother looking over on this side. We're interested just in the part that we've grabbed. So we're not going to worry about the negative 3 part. But we get a place at x equals 3 where the derivative equals 0. Now, what would that look like? If the derivative of a function were equal to 0, what would that look like topologically or topographically? Flat. It's going to be flat. That means if the slope of the tangent line would be 0, which is horizontal.
Good job.
Well, where is that on my graph? It's got to be right there, doesn't it?
Approximately, yeah.
So that's significant, right? If I want to find out where a relative maximum is, one place that could be happening is where the derivative is equal to 0, because that's a place where we get a horizontal tangent line. And wouldn't you agree that any smooth-featured hill has to have a horizontal tangent line at its peak? Right? Okay. Let's look at another one. What about the minimum? Okay, we could do. You're right. What about we can't slight the minimum? Sure. Let's look at
It has a
another one.
minimum on the other side. When the curve goes the other way.
Oh, check this out. This is going to be cool.
What are you doing?
Watch this.
Oh, that's a good line.
It's a great line, but then not only is it a great line, watch this. Oh,
you're going to turn it, aren't you?
This is just so cool. I'm going to
Flip it.
do one of those guys.
Ooh. Oh, that was badass.
I love this. I love putting toys up here. Let's get started. Okay, so I've got an absolute value function. F of x equals absolute value of x. Okay, now let's calculate the derivative of this thing, right? So if f of x is absolute value of x, then that's the same thing as saying f of x equals the piecewise function when x is greater than 0. When x is positive, what's the absolute value of x equal to? You got it. When x is negative, what's the absolute value of x equal to?
Negative x.
Negative x, because we got to make it positive, right?
Teamwork.
And then in the middle, we've got the point when x equals 0,
X equals 0.
the absolute value function equals 0, right? So if I differentiate this then, what happens? F prime of x equals, what's the derivative of this part of the function? 1. So when x is positive, the derivative is 1. When x is negative,
Negative 1.
negative 1. What about in the middle?
This is something I don't think we should do. 0.
0?
No, none.
No, incorrect. That's why it's.
And hey, how come?
There's a cusp.
Well, you could. Derivative of 0 would just be 0, but it's a cusp, isn't it? Yeah, at this one point, this one doesn't, the derivative can't be defined there. Even though we have a value of the function, because at that point right there, the derivative from either side is different. It's a sharp corner, and so the derivative is undefined. Okay? So we know then that
No.
f prime of x is undefined at x equals 0. Well, now that's interesting because look, what kind of feature is that on our curve? It's a valley, right? Now this is a river valley instead of a glacial valley. It's got kind of a V-shaped valley, right? Watercark valley, but it's still definitely a relative minimum, right? So we just found the other place where a relative minimum could occur, and they're both related to the derivative. In the previous example, we saw one where we had a nice smooth feature, we had a smooth peak, and that was a place where the first derivative equaled 0, right? Second example, we had a sharp feature, right? A sharp valley, and that was where the derivative was undefined. Turns out those are the only places where valleys or peaks could possibly exist. They can only exist where either the first derivative is undefined or equal to 0. Try to think of another place. There's no way. The only places it could happen because it's a turning point. A valley is a turning point of the function. It's a place where the function goes from being decreasing to increasing, right? That means the slope is changing, right? Either the slope is changing dramatically, where the function is just broken, or it's changing smoothly, where the slope is gradually going from positive, less positive, less positive, less positive, 0, now it becomes negative. Okay? We call those critical numbers. Places where the first derivative, the x values, where the first derivative is either undefined or equal to 0, are the critical numbers. All peaks and valleys, all relative extrema, must occur at critical numbers. Are all critical numbers necessarily going to yield peaks and valleys? Can you think of what a picture might look like where we could get a sharp break or a horizontal tangent line that's not a peak or a valley?
Like a parabola.
Well, parabola is going to have a valley, isn't it?
Why?
Right? Parabola's got a valley, either a peak or a valley.
Okay.
Okay, but what about something like this? Right?
That's a cubic equation, I think.
There's a place where the tangent might be horizontal, but it's not a peak or a valley. That's a false alarm, right? That's a critical number. It's a place where f prime of x is 0, right there, for that value of x, but it's a false alarm. Okay, I could also maybe do something like, I guess, I don't know, how about
The same exact thing.
like that?
I was thinking cusp.
There's a sharp corner, but it also is neither a peak nor a valley. Right? So that's another false alarm. Okay. Make sense?
Yeah.
All right.
Very nice.
Very nice.
Look at that side.